Good afternoon, all. In the last session, we discussed a purpose of hardware description languages and what are the major milestones in the hardware description language and the levels of design abstraction in hardware description language and digital design flow. So today we will continue the digital design flow. So before we continue the digital design flow, once again, I wanted to brief out the yesterday's contents because I thought I was uh, hurry to complete the contents in yesterday. So today, once again, I want to touch the yesterday's contents, and then we will continue the digital design flow. So introduction to the hardware description language. So here the HDL is an acronym for the hardware description language. HDL is an acronym for hardware description language. It is a programming language which is a software tool which describes the digital system hardware, which describes the digital hardware here. What is the purpose of hardware description languages? The purpose of hardware description languages is to describe the digital system or to describe the digital circuits using the text-based language here. So usually here we will have the different types of the languages. So some programming languages may be the graphical representations. So one of the example to that language is LabVIEW. So in the LabVIEW, we will use the graphical representation language to design the systems. And here, the hardware description language, HDL, is a text-based language here. It is a text-based programming language. So the main purpose of this hardware description language is to describe the digital circuitry using the text-based language. Using the text-based language. So here the HDLs, hardware description languages, describe the digital systems. So here the digital systems may be a small digital system or a simple digital system to a very large digital systems or even the complex digital systems. So the hardware description languages, they describes the digital systems, large digital systems without the need for the schematics here. Even if we wanted to describe the large digital systems with the help of the schematics, so which is very impractical, which can become very impractical for the designing of the very large design systems here, because a simple and the smaller digital circuits can easily be described with the schematic representations. With the schematics, we can easily design the systems. Whereas, if you wanted to design a large digital system or a complex digital system, so in that cases, we cannot describe the system with the help of the schematics here. Example, computer. So if you take the computer design, or if you take the CPU of the computer, so when we want to describe the CPU of a computer, so we cannot describe the entire CPU with the help of the schematics here. So that's why, so we will represent the CPU with the algorithmic level. So we will represent the CPU of a computer at the algorithmic level. So where in the algorithmic, we will use it to represent the CPU of a computer with the help of a block diagrams. So that's why when we say about the CPU of a computer, we use it to represent with them a blocks. So such blocks are called the schematics for the CPU of the computer. So the large digital systems cannot be described with these schematics. But the hardware description language can describe the digital systems without the schematics, because we use it to describe the systems with the help of the schematics. Any digital circuit is used to describe with the schematics. Manually, if you design a simple circuit or a complex circuit, we use it to describe with the schematics. But for hardware description language, it doesn't require the schematics here. It doesn't mean that completely it doesn't require the schematics. So it will use the schematics, but for describing of the digital system, it doesn't need the schematics here. It use still the schematics are used, but so they will be used in the lower level of the abstraction, not at the higher level of the abstractions. So using this hardware description language, a very large and complex digital system can be efficiently designed with a top-down methodology using the hardware description language. There is a hierarchical approach. In the hardware description language, there is a hierarchical approach. So using this top-down methodology, you can design a very large and complex digital systems efficiently. So that is one of the benefit, that is one of the advantages with these hardware description language. So you can easily implement the complex or a very large digital systems. In fact, the current the hardware description languages, as we stated yesterday also, so they are so am I audible? Am I audible?
Yes, sir. Yes, sir.
Yes, sir.
So the large and complex systems can be effectively and can be easily described or can be designed using the top-down methodology in the hardware description languages. So here the hardware description languages are the current industry standards for describing and designing the digital systems. So here the hardware description languages, they are supported for the logic simulation. So actually at the time of the introducing the VHDL or the first version of the VHDL devices or the VHDL tools, so they were only with the documentation of the circuit, and they are with the only the logic simulation only. So they are with the only logic simulation. So here the hardware, using this hardware description languages, we can model a circuit at different levels of the abstraction. You can model or you can design the system at system level. You can model the system at the algorithmic level, and you can also model the system at the gate level. So likewise, so here the hardware description languages, which allows us to design the system at different levels of the abstraction. But in the first version of the VHDL tool, so they were only for two purposes. The one is for the system documentation, I mean the digital circuit documentation, and for the logic synthesis or logic simulation. It is for logic simulation. But later, the logic synthesis tool was developed, and it was modified to use it. It is modified and it will be used for the hardware description languages. So in the earlier only, only for the documentation and for the simulation. And after the logic synthesis tool were developed, so this tool also added to the VHDL tool. And finally here, the hardware description language for the three purposes. One is for documentation purpose, whatever the circuit you have described, so that can be documented, and you can test the behavior of the digital system, so that is the simulation, and you can synthesize the digital circuit. Actually, the digital system is described in the it will be described in the form of the text-based language. So when it is in the coding form, when the behavior of the circuit is described in coding, so now that code has to be translated to the gate level here. So that is what we call the synthesis. So in the synthesis, it converts the higher English statements, or it converts the text-based system description is converted into the gate level of the system. So where in the gate level we can use the different logic gates to build the real-time hardware circuit. Actually, that is the meaning of the synthesis. So it converts the higher level document, it converts the higher level description to the gate level description of the system. So earlier it is only for with the two, documentation and simulation. There were no logic synthesis. But after development of the logic synthesis tool, so now the HDLs are capable of automated synthesis. So in this automated synthesis, the hardware description language allows the CAD tools to describe the digital system. It takes the functional description of the digital system and automatically create the gate level circuit. If you take any real-time hardware system, or if you take any real-time hardware where you will find inside, you will find a PCB circuit or a PCB board. So on which that PCB board we will have the digital circuits and digital components which are interconnected. So that is the real-time hardware module. So now the hardware description language has to translate the documented description to the gate level circuit. So that is possible because of the logic synthesis here. It is because of the logic synthesis. So the HDLs also evaluated for support for the automated synthesis. So which means that so the CAD tools will directly take the functional description and they will automatically convert it into the gate level circuit here. So that is the advantage of the hardware description language. We need not to think on the components at the gate level circuit. The hardware description language will give you the gate level circuit directly. So that is the purposes of the hardware description languages. So simply it is for to designing the digital systems at different levels of abstraction, and its support for the automated synthesis. So that's why we use the hardware description languages. So now coming to this hardware description language. So here the history of the VHDL, if you see, because our entire subject is based on the VHDL. So that's why so here we will see a short brief on the VHDL history. So here the first VHDL tool was initiated by the Department of the Defense. So that is the US Defense Department. So the US Defense Department initiated a program called the Very High Speed Integrated Circuits for their military applications and for their defense applications. They wanted to have a very high speed integrated circuits so that they can have the better devices for their defense and military applications. So the US Defense Department initiated this VHSD program here. So for this VHDL, for this very high speed integrated circuit program, so there are number of ESC companies were involved in designing of this very high speed integrated circuit chips here for the Defense Department. But at the time, most of the companies, they were using the different hardware description languages to describe and develop the integrated circuits here. So every supplier or every vendor has their own hardware description language, and they use it to develop and they use it to describe and develop their ICs with that hardware description languages here. So there are different companies were participated, and all the companies, most of the companies, they have their own differential, they have their own hardware description languages for describing and designing the hardware circuits. So because of that, all these vendors have provided the different integrated circuits in different hardware description languages here. So which means that, so one vendor has developed an integrated circuit with a specified with a specifications for an IC, and the same kind of device is developed by the other vendor with the other different specifications here. So now there is no compatibility with the suppliers here. There were no compatible with the vendors here. So that's why, so there was a lack of these standardizations in the hardware description languages. So since the vendors are developed the different integrated circuits using the different hardware description languages, so there were problem from the vendor side, and as well as there were problem in from the Defense Department also. So from the point of the vendors, so if they wanted to reproducing any of the obsoleted devices, so it was a problem for them to reproducing the devices with the different hardware description languages, because one company uses one hardware description language, other company uses the another hardware description language. So because of that, so there were a problem of reproducing of the devices. And what is the problem from the point of the Defense Department? So from the Defense Department, if they wanted to reprocure the devices, or if they wanted to reuse the devices which are damaged, okay, so for them, so it is very difficult for them to select the integrated circuits here, because one company is provided the one type of integrated circuit and another vendor provided the another type of the integrated circuit, because of they are using the different hardware description languages. So there were a lack of the standardization in the hardware description language. If they have standardized hardware description language, so then so they can have the compatibility, so that it will be useful for that the Department of the Defense. So the Department of Defense thought that, so they wanted to have a standardized hardware description language for designing of the digital systems, for documentation of the digital systems, and for the verification of the digital systems here, for design, for documentation, and for the verification of the digital systems. So for that, so the Defense Department had contracted with the three companies, the Texas Instruments, contracted with the three companies, Texas Instruments, IBM, and the Intermetrics. So the Defense Department contracted with these three companies to develop a standardized documentation tool. So these three companies worked together and they have developed, they have provided a standardized hardware description language. So that hardware description language have the interfacing, so that will provides the details of the interfacing of the input and output, and as well as the behavior of the digital systems here. So so this is all initiated in the year 1983. So in 1983, so the Defense Department of US sponsored for this project here. So the first version of the hardware description tool was in the year 1985. So that is called the VHDL. So VHDL, V hardware description language. So that here the V stands for the very high speed integrated circuit hardware description tool. So this is the first version of the VHDL tool. And in order to gain the widespread of adoption and to ensure the consistent use of across the industry, the VHDL tool, I mean the VHDL company, I mean that the Department of Defense, so they were transferred this VHDL tool for the IEEE standardization. So here in the 1987, the first IEEE standardized VHDL tool was released, and it was titled with the IEEE 1076 here. So this was the first IEEE standardized VHDL tool. And in the 1993, the revised IEEE standardized tool was released, and with the title, and it was titled IEEE 1076-93. So after the first version, so they have the feedback, they had the feedback, and they have modified major modifications. They have made the major modifications, and they released the revised IEEE standard version of the VHDL tool. So that is in 1993, the standards are known as the IEEE 1076-1993. And in the present today, so the most recent VHDL standard is that we consider is the IEEE 1076-2008. So this is the simple evaluation of the VHDL tool. So it is all from the project of the very high speed integrated circuits. So from that program, the VHDL tool was evaluated here. So the first version is in the year 1987, and the second version 1993, and the later version was in the year 2008. So even currently also we are using the same standards 1076. So in the last class also we have seen this diagram. So where from this diagram you can observe what are the major milestones in the digital logic and hardware description languages. So let's have a look on this hardware description language, because at the theory and technology these points might be familiar to you somewhat. So here how the hardware description language is evaluated here. So the first thought was in the year 1983, because of the DOD, the Defense Department has initiated and it has sponsored for the project of the very high speed integrated circuits. So from this the VHDL is realized. From this the VHDL is developed, very high speed integrated circuit. So and parallelly in the same year we have the Verilog HDL. So the Verilog hardware description language is independent of the VHDL language here. So the Verilog is different and the VHDL is different, but both are the hardware description languages only. But in the earlier version of the VHDL tool, we were only for the documentation and only for the logic simulation only. There were no logic synthesis, the first tool, but in the first version. So but later they have added the logic synthesis tool. So now together the logic synthesis tool and the early version of the VHDL together, they have released the IEEE standard version VHDL tool. So the IEEE standard version now it can design the system. I mean that it will describe the system and it will simulate the system and it will synthesize the system. And parallelly here we have the IEEE standards for the Verilog also. So here the first IEEE version, I mean the standardized IEEE Verilog is released in the year 1995. So in between that, the 1993, we have the second version of the IEEE. And okay, so these are all the milestones as far as concerned with the hardware description language. The CAD tools are nothing but what? The computer aided design tools are nothing but the software tools, so which are used to getting the devices into the real hardware devices. And the next one is very important. One is the hardware description abstraction here. So why this hardware description language here? Why it is developed here? So the hardware description languages are developed. They are meant for to describe the digital systems, to modeling the digital systems, or to designing the digital systems. So why we develop this hardware description language? For describing or for designing of the digital systems. So here the hardware description language is able to model the system at different levels of the abstraction. So these are all the levels of design abstraction. Or you can also say that it is in a hierarchy. So how a digital system can be realized, how a digital system can be realized. So in this levels of design abstraction, if you see, so it has a system level, algorithmic level, register transfer level, gate level, circuit level, and the material level. So 6 levels of abstraction here. So using this hardware description language, you can describe or you can design a system, a digital system at the system level, or at the algorithmic level, or at the register transfer level, or at the gate level. You can design the digital system at any one of the level. Where the HDL, it cannot be used at these two levels here. At the circuit level and at the material level, the hardware description language cannot be used here. Why so? Because if you wanted to describe, describe a digital system with the help of these circuit components, it is very impractical. It is not possible to describe a computer CPU with the help of the transistors here, because there are billions of the transistors here. So you cannot describe all the billions of the transistors for the CPU of a computer here. So that's why at the circuit level, at the material level, the HDL abstraction cannot be realized here. But for system level, algorithmic level, and for the register transfer level, for gate level, we can realize or we can describe or we can design the system here. Okay, so to understand this, the HDL abstraction, so the first one is the system level here. So at this level of the system, you can describe the behavior of the system in terms of the specifications here, in terms of the specifications. So what we want to design, or what digital system we want to design, so that can be at the system level here. So which means the behavior of the system is described in terms of the specifications here. For a complex circuit like a computer, if you take, so how many number of instructions can be executed per second, that is a system level specification. So how much speed is the system level specification. Okay, and the power consumption is a system level specification. So at the system level, you can describe a digital system by or in terms of the specifications. And the second level of the abstraction in the HDL is algorithmic level here. So in this algorithmic, the specifications to be broken down into subsystems here. For example, I want to design a CPU of a computer here. That is the system level design. That is the system level design. Say Example to that, CPU of a computer. So the computer of a CPU will have the specifications here. The address bus, the size of address bus, size of data, the speed of the CPU. So these are all these system level specifications for the compute, for this CPU of computer. So now the algorithmic level, so where the specifications of the system level are broken down into the subsystems here. So which means that the entire digital system which is described at the system level, that will be now divided into subsystems here. So now in this case, you take the same example CPU of a computer here at the system level. So now at the algorithmic level, now the CPU will be divided into subparts here. What are the parts here? The subparts here, arithmetic logic unit and the control unit here. So these are the subparts of the system here, which means that the specifications of the system level are described into the subsystems here. And now the next level in the abstraction of HDL is the register transfer level. So now what does this register transfer level here? At this level, so this level describes the data. It will describe about the data. So how the data is transferring between the subsystems and within the system here. So from the, with respect to the CPU, how the data is manipulated, that can be described by the RTL, that is register transfer logic, or even the at the algorithmic level also, it describes the data movement. So how the data is transferring from one subsystem to other subsystem or within the system. So which means the register transfer level, it simply describes about the data movement in the systems. And then one level down to the register transfer level, that is gate level here. So let's see example to this register transfer level. So now we have the arithmetic logic unit and control unit here. So now how the data will be flow or how the data will be moved between the ALU and CPU means, so here we will have a bidirectional signals. Which means the control unit controls the arithmetic logic unit. And where the arithmetic logic unit will have the address bus and data bus, isn't it? And the internal buses are there for data manipulation. So these are all register transfer level. So they will describe how the data is moved in the systems. Now the next level is gate level. So in this gate level, the design is described by using the basic gates and resistors. So at the system level and at the algorithmic level, we have only the block diagrams. We don't know what are the exact components in that CPU block or in that arithmetic and control unit blocks. So now the gate level describes the what are the components are there in the system and what are the components are required to build that the CPU, which in turn the arithmetic logic unit and the control unit here. So therefore the gate level, so at this gate level, so it describes about the basic gates and the resistors for to store the data. And the next one is the circuit level here. So for this circuit level, it describes the operation of the gates using the circuit elements here. So the circuit elements are the transistors, or connecting wires, are the other circuit elements such as the resistors or the capacitors or any other circuit elements which are required. So the circuit level which describes the operation of the basic gates and which describes the operation of the resistors with the help of the circuit diagrams. And now the bottom level, I mean the last level, material level. So in this material level, it describes about the materials. So it describes about the materials of the combination of the materials and how they are combined and how they are shaped into the transistors or into the connecting wires or into a diode or into a resistors. So how the materials are used to are used to shape the transistors and wires and other circuit elements. So these are all the different levels of the abstractions in the hardware description language: system level, algorithmic level, resistor transfer level, gate level, circuit level, material level. As I said that in the last slide, so here the hardware description language can be used to design a system at any level of the top four here: system level, algorithmic level, resistor level, and gate level. So you can describe or you can design the digital system at any of the level using the hardware description language. But we cannot design a system at the circuit level and material level using the hardware description. So why I am stressing on these levels of abstraction is, if you understand the hierarchy of the designing process. Let's see here, what is the top level of the design here. The top level of the design is system level design. The top level of the design is system level. The top level is system, because there is a hierarchy here. So what is that hierarchy? So this is the top level of the hierarchy, and it is the down or the bottom level hierarchy here. Top and down. So as I said that there is a top-down methodology used to describing or designing the digital systems in the hardware designing. So that top to down is this one, the levels of abstraction here. If you understand this, you can easily understand the design flow of the digital systems. You can easily understand the design flow of the digital systems. So at the system level, we will specify the specifications, what we want to design. At the algorithmic level, we will split the specifications into block diagrams here. And at the resistor level, we will give the data flow directions here. How the data has to be transferred, or how the data has to be moved in the system. And the next one is the gate level. So at the gate level, we use what are the required basic gates to build that system. And at the circuit level, it is easy, because whatever the gates and circuits you have used at the gate level, so they will be described with the in terms of the circuits here. And the last level is material level. What are the materials used to have the transistors and the diodes and the resistors? So this is the hierarchy of the HDL, or the abstractions of the HDL here. Using this, we will explain the next one here. So I will skip this slide here, and coming to this one, digital design flow here. So just recall or remember the levels of the HDL abstraction. What are the levels of the HDL abstraction? First, we will have the specifications, that is the system level. Okay, so in the design flow, in the digital design flow also, first we will define the specifications, what circuit we want to design, or the circuit which is to be designed. And once if you have the specifications, then we will go into the algorithmic level. So in the algorithmic level, you will have the block diagrams, or you can also have the block diagram. So here we will have the block diagrams. And so from that block diagrams, so then we will go for the synthesis here. So in the synthesis, we will use the digital design procedure. So like in your STL, if you see here, so we have realized the systems using the JK flip-flops, or having the truth tables. You have realized the final end circuits, or by using the truth tables, or by using the corner maps. or by using the McDonald's, by using corner maps. So you are simplifying the Boolean functions, and finally you are obtaining the logic circuits here. So that is all and comes under the synthesis process here. And once if the synthesis process is done, I mean that if you realize it, if you get these block diagrams into the circuit state, circuit level, I mean that gate level, so then we will go for the technology mapping here. So simply, which means that so the block diagram will be converted into the gate level circuit. You know what are the gate level abstraction? In the gate level abstraction, we will have the logic gates and resistors. The circuit will be represented with the gates and resistors. So at the initial, we don't know what is the circuit, but we have the specifications, and from the specifications now we are realizing the circuit. So that is with this synthesis here, the synthesis will convert the block diagram into gate level circuit. Once if you have gate level, then we will go for the technology mapping, what type of logic gates we wanted to use to build the circuit. And after that, we will take the place and route, how to place the devices in the system, so that you can reduce the propagation delay, transition delays, because the speed will also depends on the connecting wires here. If we have a too much of lengthy wires, the speed will also the delay will be more for the circuit. So that's why we have to place the components on the the digital logic gates in a proper sequence. And then the verification here. So once after placing and routing is done, which means that connections are done. So once if the connections are done, then we will verify the circuit here. And if the verification is okay, or if the verification is with the proper expected values, then we will go for the fabrication here. So to understand this, we will see an example here. So this is the classical design flow. This is the classical design flow. In this, if you see here, specification. So what do you mean that specification here? I wanted to design a prime number detector here. I wanted to design a prime number detector. I wanted to design a prime number detector. And that takes only the numbers between the 0 to 7 only. So it takes only the decimal numbers 0 to 7, and the circuit should have a delay less than the 200 nanoseconds. So this is the first step, system level abstraction specifications. And once if you have the specifications, now you are getting into the functional design here. So what do you mean that functional design? Where you will have the block diagram here. So the entire system is represented in a block diagram. It has the 3 inputs and a single output here. What are the 3 inputs here? The 3 inputs are to select to accept the input between these 0 to 7, decimal 0 to decimal 7. So for that, it need to have the 3 inputs and a single output here. So to select the prime number, if the given input, if the given number is a prime number, then the output is set to logic 1. If the given number, if the given logic number is not a prime number, so the output is set to 0 here. So you have a 3 inputs. So with the 3 inputs, you can have the possible of 8 possible inputs, and these 8 possible inputs. So from the 8 possible inputs, these 2, 3, 5, 7 are the prime numbers here. So for that only the output is set to logic 1, and for the other states it is set to logic 0. So this is our description of the circuit, the behavior of the circuit. What is the behavior of the circuit? When you apply the 0, 1, 0 input, it is the decimal number 2. So that's why it has to produce a logic high output state, so that we can understand that the given logic number is a prime number. If the output is 0, for the given combination of the input, the number is a non-prime number. So first we will specify the specifications and then we will describe the functional design. So in the functional design, you will have a block diagram or you can have a truth table also, because the truth table describes the behavior of the circuit. And then synthesis here. So here the synthesis means what you are doing exactly here. In the synthesis, you are minimizing this truth table into the circuit form here. You are minimizing the truth table into the circuit form. That is called the gate level abstraction. So at the initially you have a block diagram or you have a truth table, but you don't know what is the exact circuit to design the system. So now in the synthesis it translates the block diagrams or the truth tables into the circuit level. So now the circuit consists the digital gates here. It consists the digital gates. So what you are doing in the synthesis, you are minimizing the logical functions. You are minimizing the truth tables. You are minimizing the block diagrams, and they are getting into the circuit diagrams. And once if you have the diagram, then we will use the technology map. What do you mean that technology map? What type of logic family has to use? Is it the CMOS or a bipolar or a bi-CMOS? So now the most commonly used is TTL or the CMOS. So you will take according your wish. So we will take the logic gates here. And once if the logic gates have selected, once the logic gates have chosen, then we will go for the place and route. So we will place these gates such that the minimum propagation delay, so that if the delay is less, then the output will be fast. So that we will place these devices in a sequence and then we will connect. So once if the connections are made here, then we will go for the verification here. So in the verification, what we will look at for the verification, we will look at for the verification whether we are meeting the specifications or not. What are the specifications here? We wanted to design a prime number circuit with the delay less than the 200 nanoseconds. So in the specification, we will check the output, whether the output is having a propagation delay of the 200 nanoseconds or not, because the speed is very important. ఎందుకని ఇక్కడ మనం ఇచ్చిన specification 200 nanoseconds కాబట్టి. So one can choose the other specification also. So now we will verify the functionality of the circuit, whether the circuit is capable of producing the output less than the given delay time. If it is producing, then it is fine. I mean that it is verified with the desired output. If it is not, then what we have to do again we have to go back to the place and route, such that we have to arrange the devices in order to get the least delay from the circuit. So the placement and route is important. And once if the verification is done, then we will go for the fabrication. In the fabrication, what we will do, so we will take a PCB layout on which we will place the components, and we will connect the devices according to the place and route specifications. ఇక్కడ ఏదైతే మనం అనుకున్నామో ఆ విధంగా ఇక్కడ సర్క్యూట్ ని కనెక్ట్ చేస్తాం. So these are all the traditional way of the digital design flow, or a classical digital design flow here. So most of the time manually we are involving, physically we are involving to do all this process here. But in modern digital design, you will have the same steps here. What is the difference here? The difference between the classical and the modern digital systems is, so in the modern digital systems, so we will use the CAD tools here. We will use the CAD tools, which are the hardware description languages. So we will use that CAD tools. So at the every level of the process, see this. So initially we will specify the specifications, and from the specifications we will prepare the truth table at the functional design, and in the truth table we will go for the simulation. So whether we will check the whether we are getting the proper output for the given specifications or not. So if the at the functional design, if the simulation has given the correct output, then we will go for the synthesis. So where in the synthesis, what we are doing, we are converting the block diagrams into the gate level circuit, or we are converting the truth tables or state missions into the circuit level here. So that means you are having the gates and resistors here. And here again we will check the functionality of the circuit in terms of the basic gates and the resistors. Here you are testing the truth table, and here you are testing the gate level circuits. And again here you will check if the simulation gives the correct result, we will go for the technology mapping, or we will go back to the synthesis, and we will see we will see the circuit is realized properly or not at the gate level. And then at the technology level, again here we will select the type of technology here. That is, it may be of there are specified technologies in the hardware description language. We will choose one technology mapping, and again here also a possibility for the simulation to check whether the technology mapping is done correctly or not. And once the technology is also done, then we will go for the place and route. And once if the components are placed and routed, then again at this also you have a possibility to check the simulation here. I mean that you can test the placement and route. So here also, if you have the desired output, then we will go for the final verification. In the final verification, we will see whether the outputs are meeting the specifications or not. If the outputs are meeting the specifications, then we will go for the fabrication process. So then we will fabricate the digital gate on the semiconductor material. So here the advantage with this modern digital flow is we are using the hardware description languages. So the hardware description language allow at the each stage simulation here. So you can check with without the real time of the hardwares or real time of the testings, like a taking of breadboard and placing the components. So these are all not required here. So in the tool itself, we can check the functionality at the each stage, and if you are getting the desired outputs, then the process will be transferred to the next flow of step. So this is the modern digital design flow here. And in many of the textbooks, if you refer, this is the steps in HDL based design flow here. So don't get confused here. These two are same here. Just have a look here. You have a specifications and functional description. What you will have the functional description, you will have the block diagrams, right? So this is the usually you can refer in any textbook. This is steps involved in the HDL based design flow here. So this is very simple one. You will have the block diagram or the truth table, and from the truth table you will write the VHDL code, and you will check this VHDL code at the compilation, and in the compiler it checks the syntax errors of the coding, and if everything is correct, so it will give the no errors. So then it will go to the simulation and verification. If there are any errors in the coding, so that will be back to the coding section. So again we will modify the code and we will compile it. And once if the compile is done with the correct, then it will go for the simulation here. So in the simulation here you can test for the functionality here. So you can test before going into the gate level, you can test the functionality of your digital system by using the simulation. So all these are known as the front end steps here. Front end steps. So front end steps means you will describe your system in terms of the block diagram or truth table. and then you will write the VHDL code. And once if you have written the VHDL code, then you will compile it. And once if the compile is done, then you will simulate the VHDL code for the functionality verification. These are all called the front end steps here. And there are the back end steps here. Look at the back end steps. So what are the back end steps here? The back end steps comes from the gate level circuit here. So whatever the VHDL code you have verified at the front end, so that will be translated to the gate level here. That will be translated to the gate level using the synthesis. Once if the gate level is circuitry is converted, then we will look at the fitting. I mean that for the placement and routing. Once if the components are properly placed and once if the connections are routed, then we will go for the verification here. So what for this verification here? To check the timings of the circuit, whether we have the desired propagation delays or not. So for that you can have again the verification here. So in the hardware, in the design process, again you could see that the front end steps and the back end steps here. What are the front end steps? Always the front end steps will have that you can represent your digital system in terms of the block diagram and truth table. Once if you have defined the truth table or the block diagram, then we will write the VHDL code. After writing that VHDL code, we will check these errors for the VHDL code, and then we will check the functionality of the VHDL code, whether the code is working correctly or not. If the code is properly working, then we will convert that VHDL code into gate level, that is back end process. Once if the top end process is correctly done, then we will come to this synthesis in the back end. So in the synthesis, what we will do, the VHDL code is translated into the gate level circuits. So the gate level circuits furtherly be properly placed and they will be verified with the timing. So once it is all done, then finally it is go to the fabrication process. It is go to the fabrication process. So these are all the front end steps and the back end steps. So here there is no difference in the two diagrams. So till this point it is the front end here, till this point it is the front end, and these are the back end process. So these are the back end process. So these are the front end process. So you can you can follow any of the design step follow here. You can follow any of the design procedure. So in more